In the last video, we saw the list of 7 crystal systems and 14 Bravais lattices. Here is the list. We have 7 crystal systems: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic and triclinic, and we have 14 Bravais lattices represented by these symbols. Recall that P stands for primitive, which means lattice points are only at the corners of the unit cell. I stands for body centered, where lattice points are at corners as well as at the center of the unit cell. F stands for face centered, where we have lattice points at corners as well as all the 6 face centers of the unit cell. And finally, C stands for base centered or end centered, where the lattice points are at corners and centers of only 2 parallel faces of the unit cell. We ended the last video with a central question of why there are so many empty boxes in the Bravais list. In particular, why do not we have cubic C? This question is central to the understanding of this list. So, let us write down that question: why cubic C or n centered cubic is absent from the Bravais list. Answering this question will lead us to an interesting conclusion about the basis of classification of these lattices. So, let us look at what do we mean by n centered cubic lattice. N centered cubic lattice. So, here is a cube. I put points at the corners and I also put points at 2 parallel faces of the unit cell. I select the top and bottom faces. So, if I repeat this unit cell, I will generate a set of points which I would like to call the n centered cubic lattice. The question is, why is it not there in the list? Is it not a lattice? Let us explore first whether by adding these additional points we still have a lattice. This question can be better answered if we look at a few more unit cells. So, let me add a few more unit cells. So, I am just adding cubes next to the cubes which we were having in the beginning. Resulting in a 2 by 2 4 unit cells with one common vertical edge. And if I add the points where they are expected to be, so that is the corners and the top and bottom faces. Top and bottom faces. The diagram is getting little complicated, but you can imagine what we have drawn. We have drawn 2 by 2 4 unit cells each of them have points at the corners as well as point at the centers of their top and bottom faces. Now, if I shift the origin, instead of drawing my corner there, suppose these centering points themselves I take as my corners. Then you can see that the role of centers and corners have changed. In this new unit cell, what was corner of the original cell is now the end center of this new cell, and what was the end centering points of the original cell is the corners of the new cell. So, this shows that these new points which we have added, the end centering points, are equivalent to the original point. So, they do form a lattice. So, we do have an end centered cubic lattice. Is not a mistake in that sense, it is a lattice. All points are equivalent, translationally equivalent to form a lattice. Then why it is not in the list? Let us look at this once more. Let us create again two end centered cubic lattices side by side. So, they have a common face in between. So, two cubes with a common face, and if they are unit cells of the end centered cubic, and I put points, lattice points at the corners. Now, we are convinced that all points are lattice points at corners as well as lattice point at the face centers, but only one pair of face centers. So, top and bottom face center. Now, with little imagination, you can see that it is possible to select a new unit cell. So, now I am outlining in red a possible new unit cell for the same lattice. In red. So, this was the original end centered cubic unit cell. And in red we have outlined a new cell. A new unit cell. What is this new unit cell? What is the shape of this new unit cell? So, let us call this side A prime, this side B prime, and the third side, the vertical side, as C prime. So, we can quickly see that A prime, and if I call this the original cube as A, then A prime is half the face diagonal. So, face diagonal is root 2A divided by 2. So, A prime is A by root 2. Similarly, B prime is also the half the face diagonal. So, that is also a by root 2, whereas C prime is equal to the cube edge, is the vertical cube edge. So, C prime is just a. So, we see, and if we look at the angles, angles are still all 90 degree. So, we have alpha, beta, gamma as 90 degree. So, in this new unit cell, we have a prime equal to b prime not equal to c prime, alpha equal beta equal gamma 90 degree. This is a shape of a tetragonal unit cell. This implies a tetragonal unit cell. And if you look at the lattice points, you find that lattice points are only at the corners. So, this is a primitive tetragonal. So, which means what we have here is a tetragonal P unit cell, which brings us to now the question that we started with n centered cubic unit cell. We started with n centered cubic unit cell, but by a different choice of unit cell, we can describe the same lattice as primitive tetragonal or simple tetragonal. So, what shall we call this lattice? Should we retain n centered cubic or should we call it tetragonal P? Bravais obviously does not have n centered cubic, but he has tetragonal P. So, we can justify that this lattice is already as tetragonal P in Bravais list. So, we do not need n centered cubic. We can give a further justification by noting that the unit cell volume of the tetragonal P is smaller. Tetragonal P has only half the volume of cubic C. So, it is smaller. So, if I have a choice between n centered cubic and tetragonal P, I can say that I will choose a smaller unit cell which represents the lattice. If you accept this argument, then you will run into problem soon. Let us look at face centered cubic lattice. So, we are now looking at face centered cubic or cubic F. And I am again drawing two unit cells side by side. Two face centered cubic unit cell with one common face. They are sharing this middle face, and since they are face centered cubic, let me place the lattice points at all corners. All the corners are lattice points, as well as I have to put lattice points at the centers. So, centers of the top and bottom face, centers of the left and right faces, and centers of the front and back faces. And if we apply the same procedure of identifying a new unit cell, which we did for showing that cubic C reduces to tetragonal P, we identify an identical unit cell in the same process. So, red unit cell is representing our new choice of unit cell in this lattice. And now, if you look at the location of lattice points, you have them at corners, and you also have one in the body center of this new unit cell, because what was at the common face center is now becomes the body center of this red unit cell. So, which means even for face centered cubic we can select a tetragonal body centered unit cell. So, cubic F can be reduced to tetragonal I. But then why Bravais has kept cubic F? When we had cubic C, as tetragonal P, we deleted cubic C and we kept tetragonal P. But now we are able to show that cubic F is tetragonal I, but we are still keeping cubic F as well as tetragonal I. Why is this so? This is a very important and deep question, which brings us to the basic definition or basic classification of crystal systems and Bravais lattices. If we can reduce cubic F to tetragonal I, we will reduce the number of Bravais lattices to 13. So, has Bravais overcounted? This kind of overcounting is not unknown in history. There has been an instance where in 1835 M. L. Frankenheim came up with 15 lattices. Apparently, he overcounted. Perhaps he counted 3 monoclinic lattices instead of just 2. Then 13 years later, Bravais identified this mistake and gave his corrected list of 14 lattices. Without seeing Bravais' result, Frankenheim 8 years later in 1856 also corrected his own mistake and came up with 14 lattices. But as you know, now we call these lattices as Bravais lattices and not Frankenheim lattices because of his earlier mistake. So, history can be very harsh sometimes, and maybe the credit should have been shared between the two discoverers and the lattice could have been called a Frankenheim Bravais lattice. So, let us put the conclusion of this video. What we have concluded is that essentially the problem is that we are trying to classify lattices by looking at the unit cell shape. This will lead us inherently into problem, because we know that a single lattice can be represented by many different unit cells. So, once we realize this, that a single lattice can be represented by many different unit cells, we conclude that lattices cannot be classified on the basis of unit cell shapes, because infinitely many unit cells are possible. We have seen this. Are possible. But then the question is, what is the basis for classification of the lattices? What is the real basis for classification? The answer to this question is symmetry. And we will look at the concept of symmetry and how it is used for this classification in the next and future videos.